Have you ever just dreamed of a shortcut? A way to get to the other side of the galaxy in an instant? I mean, a real bridge connecting two super distant points in space-time. For decades, right, the traversable wormhole has been the ultimate sci-fi dream. But what if it's not just a dream? Today, we're going to look at a brand new blueprint that just might, make it a physical reality.
All right, so let's just dive right in. A wormhole. It's pretty much exactly what it sounds like. Think of it as a tunnel, or maybe like a handle, grafted onto the very fabric of space-time. It is, no joke, the ultimate cosmic shortcut. It could connect to, incredibly vast, totally separate parts of our universe.
But here's the big question, right? Is this whole thing just a cool mathematical trick, or could a traversable wormhole actually really exist? Well, to find out, we've got to go on a little bit of a quest. And this quest, it starts with what seems like an impossible problem, but it ends with a solution that is so mind-bending it literally connects gravity itself to the quantum world.
Okay, so our journey begins, and we hit a major roadblock almost immediately. You see, according to Einstein's theory of general relativity, the very geometry you'd need to build a stable, open wormhole, well, it seems to pretty much violate the fundamental laws of physics. So, not a great start.
It all starts with a really simple, super intuitive rule. For any tunnel to actually be a tunnel, think about it. Its walls have to open outwards from its narrowest point, right? Physicists call this narrowest point the throat. And this requirement, this flaring out condition, well, it's not a suggestion. It's an absolute, non-negotiable rule for the shape of a wormhole.
And this is where we just slam into a wall. See, to keep that throat from collapsing in on itself, that flaring out geometry, it demands a kind of repulsive gravity. It needs something pushing outwards. But Einstein's general relativity, which is our best theory of gravity, period, it tells us that for all normal matter and energy, gravity is always attractive. It always pulls things together. Always.
So, what's the consequence of this massive conflict? Well, it means you need something truly bizarre, something called exotic matter. And this stuff isn't just rare, okay? It's material that would have to weigh less than nothing. It would need to have negative energy. This completely violates a fundamental rule of physics, and in the classical world, it is an absolute showstopper. It's kind of like trying to build a bridge out of anti-gravity wood. It just doesn't work.
And for years, that was pretty much the end of the story. Dead end. But what if the problem isn't the stuff we're trying to build it with? What if the problem is the rules of gravity themselves? And this is where a huge shift in physics gives us a new kind of hope.
And here's the crucial point. It's a really clever workaround. Instead of demanding this impossible matter, what if we just tweak the laws of gravity a bit? That's the whole idea behind this new theory called FQ gravity. It basically suggests that gravity might have these extra geometric properties that we just don't normally see. So in this new picture, the repulsive force you need to hold the wormhole open, it comes from space-time itself, not from the stuff you put inside it. And that is a game changer, because it means we could build our wormhole entirely out of normal, everyday, well-behaved matter.
And look, this isn't just some vague, hand-wavy idea. Researchers have actually zeroed in on a specific mathematical version of this theory. It's a model where a key number, a parameter they call n, equals exactly 2. You can think of it like finding the one specific radio frequency that unlocks a secret broadcast. This very precise model, n equals 2, turned out to be the absolute sweet spot. It provides just the right geometric conditions to build a wormhole without any of that impossible exotic stuff.
But okay, having a blueprint isn't enough, right? A theoretical bridge is totally useless if it just collapses the second you try to step on it. So this wormhole model of ours, it had to prove it could actually survive in the real world. And to do that, it had to pass a whole series of really intense stability tests.
So the model had to run this 3-part gauntlet. First up, an equilibrium check. Basically, prove that all the forces, gravity pulling in, pressure pushing out, are perfectly balanced so it doesn't just collapse immediately. Second, a sound speed test. This makes sure that any ripples inside the wormhole itself don't just tear it apart.
And finally, the ultimate stress test. They had to mathematically shake the wormhole just to see if it could handle small disturbances without falling to pieces.
And, amazingly, the FQ wormhole passed every single test. It passed the gauntlet. It turns out the very same modified geometry that allows it to exist in the first place actively works to keep it stable. So what does that mean? It means we're not just looking at a cool drawing on a blackboard anymore. We have a blueprint for a real, physically stable object.
Okay, the fact that this thing could actually be stable, that opens the door to its most profound and, frankly, its weirdest implication. Its connection to the bizarre and wonderful world of quantum mechanics. This is where things get really wild. This whole journey, it now leads us to one of the most revolutionary ideas in all of modern physics. It's called the ER equals EPR conjecture. And this simple-looking little equation, it suggests a connection between the geometry of space-time and the weirdness of quantum entanglement that is so deep, it's shocking.
So what on earth does that even mean? ER equals EPR. Well, it proposes that a wormhole, that's an Einstein-Rosen bridge, the ER part, and a pair of entangled particles, an Einstein-Podolsky-Rosen pair, the EPR part, are just two different descriptions of the exact same physical thing. Let that sink in. This implies the very fabric of spacetime might be woven from quantum information. A wormhole isn't just a tunnel through space. In a way, it is the space, held together by entanglement.
And get this quantum bridge could actually be used for a kind of teleportation. Now hold on, this is not Star Trek. We're talking about moving information, not people. So imagine this. You've got Alice and Bob, and they each hold one mouth of our wormhole. Alice takes a quantum bit, a qubit, and links it to her side. Then she measures it and just sends the result to Bob through a totally normal channel, like an email. Now, crucially, that email part is not faster than light. But once Bob gets her message, he can use it to perform a specific operation on his end, and by doing that, he perfectly recreates Alice's original qubit. The information has been teleported.
But wait, there's one last, really subtle but absolutely crucial hurdle we have to clear. Does the very act of using the wormhole, sending that quantum information through it, does that cause it to collapse?
So here's the problem. Even a single quantum particle has energy. And, as we know, energy has gravity. So when you send information through the wormhole, its own gravity kind of pushes back. Physicists call this a back reaction. So the big question was, would this tiny little push be enough to make the whole structure unstable and collapse? Well, after running all the numbers, making sure it follows the fundamental rules of quantum energy, the answer was a clear no. The model passed its final reality check. The bridge holds.
So, this brings us all the way from pure theory back to the real world. If these things are actually out there, how would we find one? Well, we'd have to look for their unique fingerprints, their telltale signs. We'd look for how they bend light in a way that's different from a black hole. We'd search for the unique shadow they cast on the sky. We'd listen for the specific ring of gravitational waves they should emit. And we'd look for the distinct light signature coming from any matter swirling into them. Each one of those would be a clue, telling us we found something completely new.
So where does all this leave us? I mean, think about the journey we just took. We went from a sci-fi impossibility to a complete, stable, and totally self-consistent theoretical model. Now, have we built a bridge to the stars? No, but we have built a theoretical one. We've shown that the laws of physics might not only allow for these incredible objects, but that they might actually be essential, a way to connect the grand scale of the cosmos with the deepest rules of quantum information. And that means the hunt for those fingerprints, it's on.